For most of modern human history, generating power meant digging into the earth. We relied on heavy, physical fuels like coal and oil, resources that require massive extraction efforts, release harmful pollution, and will eventually run out. This diagram shows the required shift away from finite resources. On the right, we see the alternative, the sun. It is a clean, infinite natural resource that showers the Earth with more energy in 1 hour than humanity consumes in a year. This slide defines the tool we use to capture that power, the solar cell, or PV cell. A solar cell is a solid-state electrical device that converts light energy directly into DC electricity. DC stands for direct current, an electrical current that flows consistently in only one direction. You have likely used this technology yourself.
Even decades ago, engineers figured out how to use small strips of these cells to independently power everyday tools like pocket calculators, completely eliminating the need for replacement batteries. While a calculator uses a tiny strip, the physics remains exactly the same at any scale. Mastering how this single, fundamental building block works is your first step to understanding the massive renewable energy grids of the future. To understand how light becomes electricity, we have to look at the microscopic scale. The entire process relies on something called the photovoltaic effect. The photovoltaic effect is a physical and chemical phenomenon where a specific material creates an electrical voltage when exposed to light. Step 1 is absorption. Sunlight travels through space as tiny packets of energy called photons. When these photons strike the surface of the solar cell, the cell's material absorbs that raw light energy. Step 2 is generation. That absorbed energy acts like a microscopic billiard break. It knocks negatively charged electrons out of their normal atomic positions, leaving behind empty, positively charged spaces called holes. This creates what we call electron-hole pairs. Step 3 is separation and extraction. Because opposites attract and likes repel, the internal structure of the cell forces these newly freed, negatively charged electrons to travel outward through an external circuit, like a copper wire, to get back to the positive side. That movement of electrons through the wire is electricity. That is the abstract physics, but capturing this effect requires highly specific engineering. Most solar cells are manufactured from silicon. Silicon is a naturally occurring semiconductor, meaning it can be manipulated to either conduct electricity or block it, depending on how it is treated. This diagram shows the internal structure of that silicon. The cell is constructed in 2 distinct layers. On top, where the light hits, there is a very thin p-type or positive silicon layer. Beneath it sits a much thicker n-type or negative silicon layer. Where the p-type and n-type layers meet is called the p-n junction. This barrier forces electrons to travel through an external wire. A single silicon cell operating under these conditions produces an open circuit voltage of roughly 0.55 millivolts. Half a millivolt is a tiny amount of power. It won't run a refrigerator or even a light bulb. To make this practical, engineers wire dozens of these individual cells together in a continuous series. That connected chain of cells is what we call a solar panel. Now that we have a fully functioning solar panel, we need to integrate it into a real-world environment. A panel on a roof cannot plug directly into a television. It requires a sequence of supporting hardware. Let's trace the flow of power. The solar panel sits outside, taking in sunlight and outputting raw, unregulated DC electricity. That power flows down a wire and into a device called a charge controller. The charge controller accesses the system's traffic cop. Its primary job is to regulate the voltage flowing in and protect the next component in the chain, the batteries, from receiving too much current and overcharging. From the charge controller, the electricity moves into the battery bank. Solar panels only work when the sun is shining, so these batteries safely store the DC electricity, ensuring you have power available during the night or on heavily overcast days. Finally, the stored power moves from the battery to the inverter. Most household appliances run on alternating current. The inverter translates the battery's DC electricity into standard AC electricity, routing it into your home to power the load, meaning lights, fans, and electronics. This is why we call it a solar system. The panel is the generator, but the controller, battery, and inverter are the necessary translators that make the power safe and usable for daily life. This chart compares the 3 main types of solar panels available to an electrician. Depending on the client's budget and the physical space available, you will have to choose the right material for the job.
Monocrystalline panels are dark black, highly efficient, but expensive. On the other hand, the blue speckled polycrystalline panels have a slightly lower efficiency, but are much more cost-effective, making them widely popular across residential installations in India. Thin film panels are flexible, but offer the lowest efficiency. Once installed, field electricians must manage a highly counterintuitive problem. You might assume that a scorching hot, bright day produces the maximum amount of electricity. In reality, excessive heat hurts the system. Look closely at this temperature efficiency graphic. While solar cells need bright light, physical heat degrades the semiconductor's performance. As the surface temperature rises, power output drops. Beyond temperature, you must account for the angle of the sun and environmental debris. If a panel is installed at the wrong tilt, or if dust and tree shadows cover even a small portion of the surface, the total electricity generation of the entire array will fall significantly. Maximizing the energy harvested from a solar array requires precise angle calculations and active thermal management, and a consistent cleaning schedule to prevent dust from obstructing the cells. This grid outlines the versatility of PV technology. With no moving parts or fuel lines, we use it everywhere, from urban rooftops and public streetlights to remote agricultural water pumps operating far beyond the traditional power grid. It is also the absolute backbone of our space infrastructure. Orbital satellites and space stations cannot refuel with coal or gas. They rely entirely on massive arrays of highly efficient solar cells to harvest the sun's ambient light in a vacuum. This chart outlines the trade-offs. The advantages are clear: free, infinite energy with zero emissions and low maintenance. The disadvantages include high initial setup costs, reliance on weather, and the need for expensive batteries at night. Now that you've seen the internal physics and the external system, let's test your retention of these core principles. Review these self-assessment questions. Remember, a solar cell converts light directly into electricity using the photovoltaic effect. They are primarily made from silicon. Extreme heat lowers power output, and multiple cells must be wired in series for usable voltage. The shift toward renewable energy is accelerating rapidly. By understanding exactly how a single solar cell absorbs light, separates electrons, and routes power through a controlled grid, you now have the foundational knowledge required to install, maintain, and troubleshoot the modern energy landscape.